Ducks float. It's a well understood and accepted part of physics, but if you take a metal coin, throw it into a wishing well, it's going to sink. Now, it's easy to explain that based on the idea that the density of water is somewhere between that of the duck and of the metal. But then if you make a boat out of the same metal as the coin, then the boat can float. Why is that? And more importantly though, really, why is it that something with low density floats and something with higher density sinks? What we're going to look into today in this lesson video is a better understanding and explanation for what is going on. Let's look at a box underwater. What forces are acting on it? Try drawing it out yourselves. Alright, you should pause. I'm going to keep going. So, there's the weight downwards and force from the pressure of the water pushing it up, and force from the water pushing it down. I'll draw 3 arrows across the surface. There's all that water above, remember? And there's force on the side pushing it left and right. And to make it better represent reality, let's make these arrows longer due to the depth difference. Now to simplify, I could draw it again over here with just 1 arrow for weight and 1 for upthrust, the resultant force due to the water. But let's keep it complicated for now. I've got all these arrows because pressure acts in all directions. In fact, that's related to why pressure is not a vector quantity. But that's off the syllabus really. Look into tensors. Look into tensors if you want more. Now, looking at the arrows I drew for the 2 sides, the sizes of the forces match up perfectly, so the resultant force sideways is 0. However, due to delta P equals rho g delta H, the pressure below and the pressure above are different. The force below pushing up is larger than the force above pushing down. There is a resultant force from the water pushing the box up, and this is called upthrust. So this gives us a simple way to calculate upthrust. If T is how tall the box is, the pressure at the top is rho g h, the pressure at the bottom is rho g h plus T. So the pressure difference is rho g h plus T minus rho g h, which is equal to rho g T. The force is therefore rho g T A, where A is the cross-sectional area of the box. The weight acting down is mg, which is rho of the box times v times g, which is rho t ag. If I put these on my diagram, weight is rho of box GTA, upthrust is rho water GTA. So clearly, if the density of water is larger than the density of the box, the resultant force is upwards. If the density of the box is larger, the resultant force is downwards. In both cases, there is a force upwards, there always will be. So why do ducks and boats float? Well, the better question is probably how much of the duck sits above water and how much is below water. Now we've looked at upthrust and we've looked at the relationship between the pressure and the forces, and you should be able to apply that knowledge now to really understand and to explain properly the source of upthrust and what the value of that upthrust is going to be.